Can all of you see this screen?
Yes, sir.
Yes, sir.
You can see this slide?
Yes, sir.
Okay. So this is where we had left yesterday. We were discussing about the digital to analog converter, and we had done a couple of problems. And I hope now the basic concept of the digital to analog converter, how we convert from digits to the analog domain, that is clear to you. Today we will try to proceed a step further. We will proceed towards the reverse direction, that is from the analog domain to the digital domain. Now, what is the motivation for this? Why do we have to do this in the first place? If we see this slide, which we had earlier, we have seen in the framework of mechatronics devices that we have the digital computer here and we have the analog domain, the device over here. And through the sensors, the signal is to be acquired. And we have already seen the effects, the advantages of the operational amplifier. And it can be used for filtering, amplification, as well as for offsetting. We have completed amplification and offsetting, but we have not yet done filtering. So this we will do at a later stage when it is required. So once we have the signal, once we have a conditioned signal brought to the properly amplified and properly offsetted and brought to the range of the conversion, we have to make it understandable to the digital computer. So the only means for us is to use an analog to digital converter. We have already seen how we can go from the digital domain to the analog domain using the operational amplifier and the resistive network, resistive ladder sort of network. So this part we have already covered. This part, that is the digital computer, and we have some fairly reasonable idea about it. So now let us see this part, that is the analog to digital conversion. Naturally, it is the reverse of the digital to analog conversion. But now the point is that you have an analog signal and you wish to digitize it. How do you digitize an analog signal? So this is what we will discuss in our lecture. Now, if we consider a signal, let us take a window, and in this window we will take a signal. So let's say we have a window like this, and this is the x-axis represents your time scale. So you have 0 to start with, 0 seconds, let us say, and you are going up to, so here you have a time plotted here. So time, so as time increases, this is our time axis. And let's say we also have a signal. So let's say the signal is, so this signal changes with time. Let's say this is given by a function which is say v S corresponding to a particular time. Let's say in general corresponding to time t, this is the signal. So this is our signal Vs. Now we are interested in digitizing the signal at a particular instant. What do we mean by digitizing? So here, first of all, for this signal, let us say we have a range for this signal. We have a particular minimum level for the signal and a maximum level. Let us say we start from 0 volts and we go up to, let us say, VC volts. VC. So our signal is within the range from 0 to VC, and we have acquired this, let us say, from a sensor, and we have properly filtered it, amplified it, offsetted it, etc., and then brought it to this range. So now we are interested in knowing what is the digital representation of this at n of the signal at any point of time. For example, let us take at a particular time. Suppose we have, let us take corresponding to a time here. We have the value, we have the signal corresponding to this time as this is its value. Now, here let us say that this corresponds to the time t1. So what we are interested in is knowing what is the value of this signal at the time t1. Vs at the time t1. This is what we are interested in. Now, so we are actually dealing with analog to digital conversion. We also call it ADC. Okay. Now, we are interested in knowing what is the value, what is the digital representation of this signal at a particular point of time. Now, this involves certain concepts. First of all, this time t1 at which we are going to acquire the signal, we call it sampling the signal. Okay. So here we are sampling the signal at a particular time, which is t1 in this case. So the first thing is that we are going to sample the signal at the time t1. Because we are interested in knowing what is the value of this. So we have to sample it, sampling the signal at t equal to t1. Okay. So this is our first thing which we have to understand. This is called sampling. Now, how is this? What do we do in this sampling? There is a process, and we can use an op-amp circuit also to do this sampling. Now, even if we do the sampling, we have to capture this signal at this point of time. But then the process of analog to digital conversion, depending upon the technique that is used for it, it takes some time. There are very fast methods, but if we go for a method in general, the process of analog to digital conversion takes some time. Now, during this time, it is possible that the signal would change its magnitude. And that means if we proceed with the process of the conversion during this duration, we will we will not be able to sample, we will not be able to know the digital representation at the time at which we have sampled it. So what is done is we have to hold the signal. So you just don't sample the signal, but you also hold it. So we make use of a circuit which is called as a sample and hold circuit. Okay, and this is also realized using operational amplifiers. So it's called sample and hold circuit. And so we have to sample the signal and hold the signal. Okay. And we have to hold it till the process of the conversion is completed. So it has to be held now. This may take a very small time, but all the same, time is required. So hold the signal till the process of conversion is completed. And now comes the stage where you're holding the signal, but then you have to now represent the signal. Now you have to digitize it. So what is the digital representation of the signal? So digital representation of the sampled signal. How do we specify it? And here is where the crux of the problem lies. So digital representation of the sampled signal. How do you do this? Now, naturally, since you are representing the signal in the form of digits, you will have to choose how many bits you wish to represent the signal in. So you could represent it. So the question arises, how many bits are needed for this representation? Okay. So we have in general devices available, chips available, where you can digitize a signal maybe in 8 bits or 12 bits, 16 bits. Okay. Maybe higher ones are also available, 32 bits, 24 bits and 32 bits, but they would be very, very expensive. As you proceed from the lower number of bits to the higher number of bits, the cost of the device, the cost of the chip would increase. And you will see why that happens. Now, there are certain methods for this conversion. So the methods or the techniques for this conversion, so what are these methods for uh, the analog to digital conversion? You have several methods. Okay, we will see just a few of them just to give you an idea. We'll start with the most simple one, which is called as the ramp method. Okay, it's just a slope integration method kind of, but we call it as the ramp method. And it will be clear to you why we call it the ramp method shortly. The second method, which is very popular, which is low cost and has many benefits, but it takes, of course, it takes lesser time than the ramp method, is the successive approximation method. Okay, we call it successive approximation method, and we will discuss this in quite some detail, maybe in today's class or in the next. And we have a very fast method, in an instant method, which is called as a flash conversion method. Okay. So flash conversion, flash ADC method. So we still have more methods. Let us just have a look at these three. The first one is not used much, but the second and the third one are quite common in daily applications. Um, the second one is fast, but the third one is almost instant. Okay? The techniques are different. So let us have a look at uh, the methods. Let us start with the ramp method, and for this, so let us save our lecture first. Uh, Now I will take this diagram itself, and maybe I will just slightly modify it, what we are interested in and how are we going to achieve it. So I have prepared a table sort of. Let's make use of it. So we are going to represent, this is just an example. Okay? So we are going to represent these values in terms of 4 bits, just to start with, as a simple example. So here, let's just this height. So So you can see that uh, we are interested in the digitization, and this corresponds to a particular level. So let's say we have different values. We go from yeah. So let us say this lowest level corresponds to 0. So here we are actually talking of the representation of our signal in terms of 4 bits. Just a nibble. Just this is because it's just an example. When we double it, we will have a byte. So in that case, we can represent our sampled signal in terms of a byte. But just for you to understand this, I'm just taking a hypothetical example where we have bits of representation like this. So here, the next level is 0, 0, 0, 1, 0, 0, 1, 0, and we proceed in this manner right up till 1, 1, 1, 1. Here we will have 1, 1, 1, 0. Here we'll have 1, 1, 0, 1, and so on. So we are just progressing from here to here. So here the value is actually just 0. The digital representation is just 0 decimals. This is 1 decimal, 2 decimals. So let us say that we are able to grade this in steps from 0 to 15 volts. Okay, this is just an example. So we are going from 0 volts to 15 volts. Okay. 15 volts. Now this signal, it corresponds to a particular level, and we are interested in knowing what is the digital representation. Naturally, here it this signal, it represents this value. Okay. Now it depends whether it is on the lower level or the higher level. Maybe it's more towards the lower level. So this is our signal. Okay. This is our digital value which corresponds to this level. So here this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 is 1, 0, 0, 0. Okay. We could have had any number. Incidentally, this is 8. We could have had 5, or we could have. So we have just arbitrarily chosen at a particular time, and this is what it corresponds to. So the digital representation, what we can see here in the range from 0 to 15 volts, it is actually 1000. It corresponds to almost halfway. Okay. So we are interested in knowing how to digitize our signal at a particular point of time. This is the challenge. And for that, we have these methods. The methods, uh, that is the RAM method, the SA method, the flash, and several other methods. So now let us proceed to um, this process of the ramp method. Let us understand the ramp method. Analog to digital conversion. Now here we will take our symbol of the operational amplifier. We will take the symbol of the tag. Why do we use that? Well, we have over here already tag. Let us take a better picture. Yes, we have here. So we'll copy this symbol. That saves us the labor of doing it all over again. And we'll paste it over here. That's not copied it. Why it is not pasting? Let's see. Okay, let's paste it. So we have this symbol of the digital to analog converter, and we will make use of this digital to analog converter. So let us keep it somewhere here. And we have the signal which we are interested in acquiring. So let us take also the signal that we are interested in acquiring. Let us say that the signal is available here. We will of course take this signal after proper processing it. So we'll take it after yeah. And we're also going to sample it. So we're going to sample it and hold it. Okay. So I'm just writing it using a box. So this is our sample and hold. We'll call this as sample and hold. So our signal is here. We are sampling it and holding it, and then we are obtaining this signal. Um, Now let us say, just as an example, in the range of 0 to 15 volts, let us say that we are able to produce digital to analog voltage steps in steps of 1 voltage. Let us say we are able to go from 0 volts when all these bits are 0, and we are able to go up to 15 volts when all these bits are 1. Okay, so it's a 4-bit digital to analog converter. Uh, in this example, just to illustrate the ramp method of conversion. So here we will make use of an operational amplifier. We'll compare these two signals using an operational amplifier. So for that, we'll take this operational amplifier. Okay. And we have here, let us supply this signal which we are interested in acquiring to the non-inverting end, and this one to the inverting end. Okay. So here we have the output from our DAC, PDA, and here we have the held signal from here, VS. So this is obtained from, this is made available here, okay, through the sample and hold. So now uh, we will let's say just that, let's take an example to demonstrate this particular this technique. So in this example, let us say that we have a signal which is corresponding to say 5 volts, just as an example, okay, hypothetical. So we take 5 volts, and naturally, how are we going to represent 5 volts in this? It will be 0 1 0 1. Okay, so when 0 1 0 1 is sent through this, both of these will be the same and you will get it. But now, how are you going to achieve it? So when this signal is sampled and held, you will check the output of this comparator. So here you are having a comparator and you are having a circuit. So here you can check whether you are getting, if the positive end is higher than negative, then we get a 1. Okay. So in that case, we will get a 1. Okay. And it will be equal to a low. It will be 1 means high, it's going saturating towards the positive side, and otherwise it is saturating towards the lower side. We'll say that it is a low signal, that is if we have Vs less than VDA. Okay. Now in the ramp method, what happens? You start with the lowest number. So you start with all zeros first. Your signal is 5 volts, but you are starting with 0. Okay, that's the algorithm. So you make a comparison. So when you have 0, 0, 0, 0, a comparison is made, and you can see that 5 volts is greater than 0 volts. So you are not going to accept, you will get a 1, and in that case, you will say that here this has to be incremented. So you will increment it. So you will start with initially. So if Vs is greater than VDA, then you will have, that means if output is 1, okay, then you will say that and you will then increment this count. Let us say initially you start with a count of 0 initially, and then you increment this count because the output is 1. So you just increment it. So that means you just say n is equal to n plus 1. Okay. Now, and then you output the, so you take and then you output the next n. So corresponding to this, so you have incremented it. Now you output the incremented n. Through the DA. That means you are going to produce an incremented value. So next value will be 1, 0, 0, 0, 1. So you are going to send out a 1. Again, you are going to compare. And here again, the comparison says that Vs is greater than this, and so it is a 1. So again, you are going to increment it. So as long as this takes place, you're just going into this loop. Okay. So you are just going to increment it and then going on outputting it. And otherwise, you will say that Vs is either less than or equal to Vt. So this is the other condition. So in this case, the output should be zero. And you have the value of the DAC will reveal the value, the digital to analog conversion value will be N. Okay, and this is your required analog to digital conversion value. I would say rather this part, right? It has N ADC. That means the number obtained, the digits obtained after the ADC conversion is equal to N. Okay, so we went on incrementing, and then else this is then output is equal to 0, and when this happens, uh, you have to say that okay, now the conversion is complete. So what you are doing is essentially you are taking a feedback from here, depending upon this algorithm, and you are sending it again to the process of analog to digital conversion. So you are taking from here, every time this happens, you are taking from this algorithm and then you are passing this information again to the converter. So this is the algorithm for. So you can see over here that the output, which is this number which is produced finally, that is N, which actually matches this 5, or it comes, or it just is less than 5, or is just more than 5. Okay, that number is your analog to digital representation. It's the digital representation of your analog signal. So in this case, it will represent 5 volts. So here you will have, you will start with zeros, and after each step, you will come to 0. So initially you started with zeros. So first step, everything was 0. Okay. The second step, again, you sent a 1. Sorry, it should be 0, 1. Then you sent a 0, 0, 1, 0. Then you sent a 0, 0, 1, 1. Then you sent a 0, 1, 0, 0. And then you sent a 0, 1, 0, 1. And this corresponded to 5 volts. Okay. This corresponded to 4 volts. This corresponded to 3 volts. In this example. So you can see that you're going from 0, you're going on incrementing till you are equal to or near about equal to this signal. Okay. So this method is called as a ramp method of analog to digital conversion. Now you can see the pitfalls of this method. We just have a little time. I'll just quickly explain to you. There are certain disadvantages with this method. Uh, while you can set the size of the digital representation, 4 bits or 8 bits or 12 bits or 16 bits, uh, the process is going to be based on serial incrementing starting from 0. So if your signal is say somewhere towards the upper end of the range, you will have to count more. So it's going to take more time because this algorithm involves more number of steps. Okay. And if your signal is lower in magnitude, this algorithm is going to take less number of steps. So the disadvantage of this method is that it will take variable number of steps for the conversion. So this is a drawback, and naturally, this says that we are not going to have a uniform rate of uniform number of steps for a particular conversion. So this is a disadvantage certainly. Naturally, it's going to take a lot of time because if you are towards the end, you will have it could take a lot of time. So would take a lot of time for high magnitude signals. Okay. So this is a disadvantage of this method, but it certainly gives you an idea about how the process of conversion from the analog domain to the digital domain is done. I hope it's clear to you.
Yes, sir.
Yeah. So if you have any questions, please ask me. Otherwise, we will conclude our lecture for today. Anybody having any query? Okay, so I'm going to.
Sir,
Yes.
sir, if we consider a case in which our sample and hold signal is 4.5 instead of 5, then
Yes.
from 0100 or 0101, which value we will take?
Yes. So that is a good question. Now you see, it will depend upon your algorithm. Okay. That's what we just discussed. The problem with the digital representation, these are the pitfalls of the digital world, that you cannot, you are representing in terms of discrete digits. Now if you have 4.5, so you apply this algorithm, so what will happen? So here you have 4.5. So first you go up to 4. What happens is this will come 1. Okay. So output will be 1. And so you will go on incrementing. And the next, after 4, you will have 5. Right. So at 5, when you increment after 4, okay, so here you are having 4.5, here you are sending out 5. When you make the comparison, so it has to be less than or equal to DA, then your conversion is, so it will indicate that now your conversion is ready, and it will indicate a 5 volts. Okay, so 4.5 instead of so the representation of 4.5 will be 5 volts. The representation of 4.8 will also be 5 volts. Representation of 4.9 also will be 5 volts. Representation of 5 volts will also be 5 volts. Okay. So this is the problem which we have with digital representation. Okay, this discretization. Is it clear?
Yes, sir.
Okay. So any other question? Shall we conclude for today?
Yes,
Okay.
sir.
Okay. So we will end our lecture for today. Thank you very much. Have a good day.